Good morning all. So today we are going to discuss the concept is called that magnetic circuit. So before going to deal with that magnetic circuit, so let me to remind you what is the electrical circuit. As we already studied what is meant by this electrical circuit, the definition is, so the electrical circuit has a closed path, has a closed path followed by the current is called a electrical circuit. So for example, what is this one is that suppose you have a simple network like this, have a different element which are connected something like this, R1 and R2, and some voltage has been given to this network. Then then the current will drawn by the circuit is I. So this current is completely circulating through this closed circuit. So this is has a closed path for the current. So you can say this is called a electrical circuit. Electrical circuit. So similarly, the same concept can be extended to the magnetic circuit here. So what is this magnetic circuit here is, so magnetic circuit. So the definition for the magnetic circuit is, so it is also has a closed path followed by magnetic flux. Magnetic flux is called the magnetic circuit, is called a magnetic circuit. So this is what the definition for the magnetic circuit. So to understand this, so let us consider a magnetic circuit. So I'm taking a simple core. I have some core, it is iron core, something like this. On this core, suppose I have a coil, the conductor coil has been connected, and this has been excited with some supply system, excited with the supply system. So therefore it is going to draw some current here. So it is going to draw some current I. So as this current is flowing through this circuit, therefore it is going to produce the flux. So this current, then it is going to produce the flux pi, and this flux will going to flowing through a closed path. So this is what the closed path for the flux pi, and this is called a magnetic circuit. This is called a magnetic circuit, because here that closed path followed by a magnetic flux. This magnetic flux has a closed path, so that it can completely can move inside this magnetic core. So similarly, the another kind of core also is possible. So that is also I'm going to show here. So this is also a core, but it is a ring type core we have. So it is a ring type core we have. On this core again we have a winding. If it is the conductor winding has been connected, and if it is excited with some AC system, so again this is the amount of current drawn produced by this system here. Therefore as a result, this is also going to produce the magnetic flux through. This is what the flux pi being produced by due to this current I is flowing through this conductor, and it is also have a closed path. So this is also you can call that a magnetic circuit. I hope you understand the definition of the magnetic circuit. So magnetic circuit is nothing but it is a closed path followed by a magnetic flux, is called a magnetic circuit. So we'll talk some important terminology in the magnetic circuit. The first terminology we're going to talk here is called the magnetic flux. What is this magnetic flux? So this is you can show with that pi is called a magnetic flux, and the unit for this magnetic flux is Weber. So this is well known to everyone. So magnetic flux. Suppose we have a permanent magnet. Suppose we have a permanent magnet like this. It is a permanent magnet. It has the north pole and the south pole if it is there. So therefore, always my magnetic lines of force, the magnetic lines of this force of lines will start from the north pole and goes to that south pole. So this is what the magnetic lines are always going to start in these directions. So this is what the magnetic lines of force you can imagine like this. But inside the inside this magnet, your magnetic lines of force will go from the south to north, but from the outside the outside of this magnet, if you see, then your magnetic lines of force will go from the north to south. So you can define here. How can you define a magnetic flux? Here is nothing but the total lines of force in a magnetic circuit, in a magnetic circuit is called as the magnetic flux. So this is the one of the kind of the definition for a magnetic flux. The total lines of force in a magnetic circuit is called the magnetic flux. Similarly, that electromagnet also can be formed. So how will you form that electromagnet? Here it is very simple. If you have a core, a core has been there. On the core, if the conductor coil has been wounded, something like this, have the conductor coils, and this conductor coil is excited with some AC system, some voltage E, then it is going to draw the current. It is going to draw the current. This is what the current I is flowing through this particular conductor, and it is what the conductor here. So due to this conductor, as current flowing through this conductor, it is going to produce the magnetic field. It is going to produce that magnetic field. That is the one of the property. So as for this current direction, so this is going to form a north pole and this is going to form a south pole. So that these are the magnetic flux lines, or you can say magnetic force lines also can be possible. So this is how it is called a electromagnet. It is called a electromagnet. Then here you can define what is the magnetic flux here. So this is also can be defined as the magnetic flux. The magnetic flux is produced due to the flow of current, to the flow of a current in a wire. Wire is nothing but a conductor, or you can say it is a electromagnet. So this is also a definition. If you talk what is meant by a magnetic flux, as I already told you that suppose you have a conductor, something like this. Suppose you have the conductor, it is the conductor, you can say, and if the conductor through, suppose this is the current direction I, then whenever this current carrying conductor is there, therefore there is a phenomena, it is going to produce the electrical field around it. So this is what the magnetic field is going to produce around the conductor. So what is the direction of this magnetic field or a magnetic flux, and what is the conductor direction? So that can be defined by, is called the thumb rule definition. If you talk what is the thumb rule here, so with this thumb rule you can able to understand what is the direction of current and flux. What is the direction of current and flux? That is what we have to understand here, because whenever the current carrying conductor is there, therefore it is also going to produce the magnetic flux around it. So you have to understand what could be the direction of the current and what could be the direction of the flux. So to understand this, this is called a thumb rule. So this is called a thumb rule here. What is this thumb rule is going to talk here? It is, suppose so this is the conductor. So this is nothing but a conductor which is held by this the right hand here. So this is what the conductor, you can say conductor here. And if this is the conductor, then so assume, so this is the current direction. So this is the current direction, you can say this is the direction of the current I. Then you can say that the thumb is showing the current direction. This thumb showing the current direction. Then the remaining fingers or remaining wrapped fingers or the remaining fingers is going to show the direction of the flux. The remaining fingers is going to show the direction of the flux. So what is the direction of the direction is showing here, the remaining finger? So this is the direction, isn't it? So this is the direction of the this remaining finger. It means this is the direction of the remaining fingers. So this is what the direction is going to be shown by the remaining finger. So this is called the remaining fingers are wrapped fingers. Fingers shows the direction of the flux. That is direction of the flux. So that is what called a thumb rule. So suppose you have the conductor, and if thumb shows the current direction, then the remaining fingers, wrapped fingers, going to show the direction of the flux, and vice versa as well. Vice versa means, suppose if thumb shows the direction of the flux, then remaining wrapped finger will going to show the direction of the current. That is also possible. So that is what you have to understand here. Vice versa property. If thumb shows, if you hold the conductor with the right hand, if you hold the conductor with the right hand with this, whatever the figure shows like this, if you hold the conductor, then the thumb shows the current direction, then remaining fingers will show the flux direction. Otherwise, if the thumb shows the flux direction, the remaining fingers will show the current direction. Vice versa can be possible. So that is what you have to understand what is meant by this thumb rule. So you can more clearly you can understand here. So this is what you can understand here. Suppose how that right hand has been hold the conductor, and then this is the direction of, so this is the direction of the current, this is the direction of the current, then magnetic field direction is the remaining fingers. So wrapped fingers is going to show the remaining fingers going to showing the magnetic field. This is the current direction I, then this is going to show the magnetic field or magnetic flux direction. This is remaining finger is going to show. Similarly, suppose the current direction is going in downward direction, I direction, this current is going in the downward direction, then the remaining fingers is going to showing this is the direction. So this is what the direction is shown in this way. Suppose just want to talk here, and I just want to see the top view of this both the scenarios here. So what is the top view? So if I have seeing from this point, so this is called a top view. If you see from the top view, then this arrow mark is going to represented with a dotted line, then this is going to represent with the dot point. It means, so the current going in the top towards the top view. So this is what the top view arrow mark is going, so that is represented with the dot point. And what is the direction is going to be showing from the top view? So this is going to showing that anti-clockwise direction. So this is the anti-clockwise direction is going to showing by the magnetic field, and that from the top view you can see the dotted point is going to show the current direction. It means that with respect to, if you talking about the digital board, if you see with respect to the digital board point of view, then dot it is showing, it means that the current is coming from towards the board, or you can say coming outward from the digital board, or we can say the current coming outwards from the digital board, and the magnetic field or magnetic flux direction is in anti-clockwise direction. So that is what the top view, if you see. So if you see from the top view, this is the top point, the arrow mark is going to show as a tip point here, isn't it? That's why I'm showing with the dot point here. So that is what I can show here. Similarly, if you see from this here top view, from this diagram, then you can say this could be a arrow point here. So this is what the look like it is. Then here from the top view, if you see this point, then this is going to look like a cross point, and this is I can say this is the direction, it is the clockwise direction of the magnetic field. It is the magnetic field, you can see this is the clockwise direction is coming. If you talk in with respect to that board point of view, then your current going inside the board, here the current going inside the board, then the magnetic field is clockwise direction. Here my current coming from that board outwards the board, then you can say this is the magnetic field direction is in anti-clockwise direction. So this is what you have to understand, what is the symbol of this one and what is the symbol of this one. Now again we'll go back and we'll talk what is the magnetic flux density here. So what is this magnetic flux density? So this is denoted with that capital B, magnetic flux density. So to understand this magnetic flux density, so let us consider a simple magnet. If we have a simple magnet, have that north pole and south pole, something like this, if you have, and as you know these are the magnetic flux lines, or you can say the magnetic flux is going to from the north pole to the south pole, is going something like this. You can imagine. So this is what the points is going to be, it is shown here. So this is what the is coming like this. In this is called that magnetic flux, or you can say magnetic lines of force. This is the flux or magnetic lines of force. You can talk flux pi. Suppose if you have create a unit area here in this magnetic lines of force, in the magnetic lines of force, create a unit area, just try to obtain the unit area. Through this unit area, how many magnetic lines of force or magnetic flux is going through this unit area? So that is nothing but a magnetic flux density. The magnetic flux density, this can be, B can be defined as the flux, that is the flux pi going per a unit area. Unit area is called a magnetic flux density. So if you draw the unit area, through the unit area, the how much amount of flux is flowing through that flux per unit area is called a, is defined as the magnetic flux density. And this is as called the Webers, can be units for this one, and this is meter square. Then flux, this magnetic flux density unit is Weber per meter square, or sometimes you can write it is a pi by area is equal to, sometimes it is written as Tesla. So this is also one of the important the point you have to understand, what is this magnetic flux density. Now after this again we will going to talk one another terminology is called magnetomotive force, is called a magnetomotive force, motive force, or you can say it is mmf. So to understand this, I will try to explain you what is the electromotive force. So first we'll go with the electromotive force. What is this one? Or you can call voltage. If you talk of the electrical circuit, you have already gone through this EMF or electromotive force. What is this? We will discuss this, then we will come for what is magnetomotive force. So what is this electromotive? Is nothing but it tends to drive, it tends to drive the current, drive the current through electric circuit, isn't it? Electrical circuit. This is called a EMF or voltage. That is what we have seen. So this is the some EMF or voltage. Then if you have a circuit like this, or then it's try to drive the some current I through this circuit, isn't it? So this is what the EMF we are talking. Similarly, same definition can be defined here also for magnetomotive force. So here it tends to drive the flux, drive the flux through the magnetic circuit, through a magnetic circuit. So this is the definition. If you see the both the definitions, both are the similar, but where we have talking drive the current here, but when it comes to the magnetic circuit, EMF, MMF is going to drive the magnetic flux. So that is what. And the MMF also can be defined as MMF also. It is nothing but, so it is N into I is called. So you can say it is the N is number of turns. So number of turns of the coil, number of turns of the coil. Suppose you have a coil something like this, 1 turn, 2 turn, 3 turn, 4 turns, 5 turn, like this. How many number of turns it has? 5 turns, isn't it? Like that, n turn. This coil can be have n turn. So this is what the n is number of turns by the coil, and I is the current. So it can be, unit is also ampere turns. Also it can be measured. So it is called the MMF. Then we will going to see what is the magnetic field intensity. Magnetic field intensity. What is meant by this? It is also denoted with that capital H, magnetic field intensity. So this magnetic field intensity is defined as, it is the magnetomotive force per a unit length, of the conductor. It's called a MMF, or you can say it is a magnetic field intensity. The magnetic field intensity can be defined as the MMF per unit length. So what is this MMF? This number of turns N into I by unit length means, suppose have the conductor length is L, or core length you can talk. It is the length of the core is L, then you can show here something like this. Then units are ampere turns per meter. So like that you can, magnetic field intensity also can be defined. And moreover, your magnetic field flux density and magnetic field intensity are directly proportional to each other. This is also one of the, B is directly proportional to H, and if you remove this proportionality constant, then there is called that mu H is going to coming here, and where mu is called the permeability, of the material, material. So what is this this is, we have to define here. So what is this one? Magnetic permeability, you can talk, it is magnetic permeability. So mu can be defined as, so it is the ability of the material, it is the ability of the material, of the material, material through which it allows, it allows magnetic lines, magnetic lines of force, lines of force. So that is the ability of the material. It will, so what kind of material, so depending upon the type of the material, the mu, the permeability of the value can be defined. So mu also can be B by H, something like. Also you can write the ability of the material through which it can able to allow the magnetic lines of force. So that is called the magnetic permeability. So we'll talk another terminology here. It is called the reluctance. Reluctance. What is this reluctance terminology? We'll talk here. It is denoted with a capital S here. So before going to talk about this reluctance, we'll talk what is the resistance. In the electrical terminology, we have already known what is this resistance. So what is this resistor or resistance R we have seen. So what is the definition for resistance? It opposes the flow of electrons. It opposes the flow of electrons or current, you can say flow of electrons or a current. So that is the property of the resistance of any material. Then if you want to write what is this, R is nothing but V by I, or you can say EMF by I, something like you can write. So R is equal to resistivity also rho L by the cross section area of the conductor. These are the concept we have already gone through in case of the electrical circuit. When come to that magnetic circuit, what is this reluctance? Is nothing but, so it is the property of the material, it is the property of the material, it opposes the flow of magnetic flux. It opposes the flow of magnetic flux. So that is the property of this reluctance. Then reluctance S can be defined as is mmf per the flux pi, you can say. So number of ampere turns n into I by flux also you can write, or ampere turns per Webers. This is the units also you can write. Then what is this reluctance? The reluctance you can write, it is L by a mu into the cross section area of that particular core. L is the length of the core and A is the cross section area of the core, and mu is the permeability of the that material, which depending upon that, and the mu is you can also write mu is nothing but it is mu naught into mu r. So this is the constant value, but this is that called mu r is called relative permittivity, relative permittivity, and this is the value of this relative permittivity is different for different materials. For example, for air, the mu r is equal to 1, isn't it? So this is like that. Also you can able to understand what is meant by the this permeability or relative permeability. Then what is this permanence here? Permanence, this is that what you can call as the reluctance. Then permanence is nothing but it is the reciprocal of your reluctance, or you can say 1 by a reluctance. So that is what the permanence is going to come. Webers per ampere turns is the units. Similarly, what is the reciprocal of this R? Is nothing but the conductance. Conductance is nothing but 1 by resistance, isn't it? So this is what you have seen, and the unit of this conductance is mho. So that is the concept you have already gone through this. So after gone through all this basic concept, I just want to see that analogous between my electrical circuit and my analogous between my electrical circuit and magnetic circuit. I just want to see what could be that analogous in both the circuits. So let us see here. Suppose I have a magnetic circuit, simple magnetic circuit could be a, this is a magnet and I have a some system, it is the MMF you can say, then this is the flux flowing through this circuit. So this is, you can say, it is a flux pi. Then what is my analogous of this one? You can say it is a very simple circuit you can show here, isn't it? It is the resistance R, current I, and this is EMF or voltage. You can talk, isn't it? So from this you can write what is this this pi here. This is pi. I can write this is MMF per the reluctance of the core, isn't it? Here if you want to write I, this is nothing but V by R or E by R. So this is how you can write. And if you want to write what is this S is reluctance, the length by mu naught mu R into cross section area. Then if you want to write what is R here, so rho L by A. So these are the different case you can understand here. It is that magnetic flux density, it is flux per unit area, where it is that electrical current density, current per the unit area. So this is, and here we have that flux, then flux pi 1, flux pi 2, flux pi 3. It means that similarly current can be have I1 plus I2 plus I3. It means that how your KCL can be also possible with in terms of your flux as well. Similarly your MMF, you can talk MMF1, MMF2, MMF3 up to so on like that. Here that electrical voltage E1 plus E2 plus E3. So like that also you can talk the relation between analogous also you can see how could be the possible relations, can able to understand what are the relations you can try to understand here. Now we'll see that another topic here. So classification of or types of magnetic circuits. Classification or types of magnetic circuits. What are the different classification we have? The first the classification is simple magnetic circuit. We have simple magnetic circuit. We have the second one is the composite or series magnetic circuit. Composite or a series magnetic circuit. Third is called parallel magnetic circuit. Parallel magnetic circuit. So these are the different types we can expect, or you can possible scenarios you can expect from this magnetic circuit. So let us will see what is the simple magnetic circuit, and then we'll see the analysis of that simple magnetic circuit. So let us consider a simple magnetic circuit. I am taking a ring type of magnet core I am taking. So it is a very simple magnetic circuit I am considering here, and I may have a conductor turns is there, and so current I is flowing through this. So therefore it is going to produce the flux through it. So this is the flux pi is going to show me. Then as we know that mm is directly proportional to pi, isn't it? So that is like in electrical circuit, V is directly proportional to I. So that is what I am writing here. So similar, if you go through the analogous of this one, then it is coming like this. Then pi also I can write mmf by the reluctance, isn't it? It is a reluctance you can write. And as we know, this is nothing but L by mu by A, and B also, mu into H. Just you just make it off, or can bring some kind of analysis here. This is N into number of turns into current. Then B, if you want, this is pi by A. So these are the some different relations we have. You can have H is equal to, you can write mmf by length of the core. So these are the different ways you can write. What is this length? Length is nothing but what is the length of this core. So that is what the L is going to show here. So this is a very simple network, simple magnetic circuit I am taken, and I'm just try to obtaining the relations between different terminologies. What are the things I have discussed in this? So next I will go with the analysis of the composite magnetic circuit. I will go with the analysis of composite magnetic circuit. Analysis of composite magnetic circuit. So here my core is not only made up of single material, my core is made up of the different materials. So that is the meaning. Composition means the complete, my core is made up of the different materials. That is the meaning of this one. Then you can see here, so I'm trying to draw this one. So this is the some core has been made up of some amount, some material, and then this is what some material. Then again this is the core, again is coming like this, and this is what my core has been made up of different composite materials. So this one is different material, but this one is different, and air gap also different material. This is what the complete composition of this circuit has been made. And assume my winding is somewhere here, the current I, then this is what the my flux direction is flowing, and completely it is going to be a closed path for my flux pi. If you see here, this material has made up to some length from here to here. This is the some length. Assume this material has a length L1, and this material has a length, assume up to this point to this point, it is L2, and up to this material from here to here, up to here to here, this material length is assume L3, and this air gap, this is also acting as one material here. This is the assume LG, air gap, length of this material, air gap you can assume, and the cross section area of this air gap is assume it is AZ, and the cross section area of this material is A3, and the cross section area of this material is A1, and the cross section area of this material is A2, assume. So these are the different ways I am assuming some concept here. Then so this is what MMF is, can try to understand here. Then the total reactance is given by, so how will you write what is the total reactance? Or you can, if you see this diagram, this is can if you draw this diagram in a electrical circuit manner, then this is coming like this. So this is my, you can say it is a mmf. This is the one reluctance, this is one reluctance, this is one reluctance, this is one reluctance, isn't it? So this is what the mmf, and this is pi. This is has a reluctance, you can say reluctance s1, this is the reluctance s2, this is reluctance s3, and this is the sg or air gap reluctance, you can say sg also, you can understand here. Then it is look like some kind of circuit here, and if you want to calculate the total reluctance here, then what is the total reluctance? S, you can write it is nothing but S1 plus S2 plus S3 plus Sg, isn't it? Because this material has some different reluctance, this material has different reluctance, this air gap has different reluctance, this is also has a different reluctance, therefore which are all connected in series. Why I am saying it is series? Because in all these materials my pi flux is constant. As the flux pi is constant, it means all the element materials are connected in series. That is why both I'm showing here. So S1, S2 and Sg, like that you can show here the total reactance, and you can derive what is this one, L1 by mu naught mu R1 A1 plus L2 by mu naught mu R2 A2 plus L3 by mu naught mu R3 and A3 plus Lg, this is air gap length, and mu naught, where mu r is nothing but 1, isn't it? For air it is 1, so I'm not going to show that one, and area is AC, and I can show this is what the total reactance. And if you want to find what is this mmf, is nothing but it is pi into the total reluctance, isn't it? The flux into this one. So like that you can do the analysis of this one. If you, whatever you want, you can do the analysis, and you can try to understand the concept here, isn't it? So this is the R, you can further you can implement this one. Then this is the flux pi. Instead of flux pi, this flux pi is going to be something like, and all this will come L1 by mu naught mu R1 A1 plus L2 by mu naught mu R2 A2 plus L3 by mu naught mu R3 A3 plus Lg by mu naught is come like this. If you manipulate all these equations, then mmf also can be writing in terms of b1 by L1 by, so mu naught mu R, something like b2 by L2, some mu naught mu R2, and plus b3 L3 by mu naught mu R3 plus bg Lg by this one, this will come again mu naught mu R, so this is also 1 here. So our further mmf also can be is in terms of the field intensity H1 L1, H2 L2 and H3 L3 and Hg Lg. So these are the different analysis, like that you can do the analysis. Because I'm doing nothing here, because I have already defined what is H and what is the relation between B, what is the relation between B and flux. So by using all these concept, I'm trying to correlating all these values here. So like this you can do any number of magnetic circuit. If it is given to you, you can draw whatever the magnetic circuit you can have. According to that you can draw the some circuit here. So I will show the some symbols here. Note, or you can take it as a note or observation. So if you have a simple network like this, have a magnetic circuit, and if you want to analyze this magnetic circuit, then you can make it into a equivalent circuit, electrical equivalent circuit, and you can analyze very easily, isn't it? So that's why I'm just want to show here. So this is a very simple network, isn't it? So this is a simple network. We have the current I and flux pi is going to be coming, right? So this is mmf, right? Mmf, how r is also, if it is something like this is there, or if it is something like this also, it is a very simple core. We have mmf and we have a current I, and this is what the flux is going to be flowing through this one, flux pi. So this is the equivalent of electrical terminology you can write here. So you can draw, this could be a equivalent uh, equation you can write. So this is nothing but your mmf, this is the reluctance, and this is the flux pi. So that is what I'm trying to show here. So reluctance R, you can say reluctance S is L by mu by A, isn't it? A, what is A? A is the cross section area of the material, cross section area of the material. L is the length. What is the total length of this material? L, or total length of this material is called the L. You can talk. So after converting this kind of material into this network, you can easily solve the network. So that is the point I just wanted to talk here. So similarly, you can, if you can see here, so have a different material, something like this. Suppose I have a material something like this. I have some kind of material. So here in between this, it is a air gap is there. So this is another composite type material. It is mmf, and you can say it is the current I is going. So this is what the complete the path for your flux pi. Here you have the two materials. So this is the material one, you can say core material. So it is the core, this is the air gap. These are the two types of the material we have utilizing here, or you can say it is a composite magnetic circuit. It is made up of air as well as the core. So how will you define this one? Or it can be similarly, it is also look like this one, right? Or it is also look like this one. So if it is something like this also, it is possible, isn't it? So this is also a possible. So this is also, you can talk, and have the current I, and this is what the complete flux direction also can show. Flux, this is the core, again this is the air gap material, you can talk. Then what is the equivalent circuit here? So again this is my mmf, and my flux is constant in the both the core and the air, so it is in series. I can show this one, right? So this is one reluctance, this is one reluctance I'm showing. This is mmf, this is one reluctance, this is one reluctance, this is my flux pi, this is the reluctance of the core, I can say reluctance of the core, and this is the reluctance of the air gap I want to show you. Then what is this flux pi? Can be written as mmf by the reluctance, so sc plus sg. So like that you can able to analyze the network. You can do any kind of analysis if you have different formats here. Similarly, the another one is called the parallel type network. What is this parallel magnetic circuit here? So this is look like a parallel magnetic circuit. So this is what the parallel magnetic circuit. Suppose you have like this, and if you have a, this is mmf, and this is what the current is flowing through this one. Therefore this is the flux, but this flux has been dividing here. So one flux is going in this direction, that is I can take pi 1, another flux is going in this direction, so I can take this is the pi 2. Here it is again it is total pi is equal to coming as pi 1 plus pi 2, isn't it? So this is what the parallel of the magnetic circuit. You can if you talk here, pi 1 plus pi 2 is going to coming. So what are the possible cores you can talk here is here. So my flux is dividing here, therefore it is a look like a parallel network here. My flux is dividing here, isn't it? My pi total pi, the total pi is going to be dividing in pi 1 pi 2. So I have to show this one electrical, in terms of electrical circuit terminology, then this could be coming like this. So this is one circuit, this is one, and this is the another I'm showing here. So like this I'm going to show here. So this is, I can say this is one core, this is the one core, S1 core. So up to this point, this one is going to be one core S1, and this one is up to this point, this is the second core's reluctance, and this one is the third core reluctance S3, just want to show here. So like that, here my total flux pi is coming, this is total flux pi, here it is divided, this is pi 1, this is pi 2, this is pi 1, again it is coming back. So pi is equal to pi 1 plus pi 2. So this is how you can convert your magnetic circuit, parallel circuit into a very simple equivalent circuit in terms of electrical terminology. Then you can by using that different relations, what are the different relations we have, by using that you can try to solve the networks. So this is the way you can able to understand the complete idea of what is this magnetic circuits and what are the analysis of the magnetic circuit for different configuration also you can do. I hope you understood this concept, and the next class we're going to see the one more concept in the same kind of topic. Thank you.